Hi friends, in this proposed class we discuss about the anti-Icelandic protection for VSM inverters in distributed generation. Let's move into the thesis. Virtual synchronous machine technology. So nowadays it is an attractive control method that is used for the inverters. Inverter side we just mentioned the virtual synchronous machine technology method control scheme. Okay. So where we proposed this entire thesis means when we integrate main grids with the microgrids, that is the major thing. When we integrate the main grids with the microgrids, at that time there will be a voltage and frequency support. For that purpose only we just proposed this VSM control strategy in the proposed method. In added with the VSM control strategy, we additionally implemented anti-Icelandic protection scheme. Okay, anti-Icelandic protection scheme for the proposed thesis. So why we preferred anti-Icelandic protection scheme means for safety concern and also hazardous cases. Why these hazardous cases will be takes place means you already know when we talk about the main grids with the microgrids, main grids having high power transfer capability when compared with the microgrids having low power transfer capability. Okay, so I need to disconnect the main grid with the microgrid. That is the case. Icelanding means when we disconnect the main grid with the microgrid. That is the case of the Icelanding detection. Okay. So for this purpose, I just using a novel hybrid control strategy. What is the control strategy using I am here in this proposed scheme means virtual synchronous machine control method with anti-Icelandic protection scheme. Okay, anti-Icelandic protection scheme. So go into through the proposed diagram. I will show you here. This is the virtual synchronous machine control strategy. All these things in this virtual synchronous machine controller, we having rate of change of voltages and active and reactive power flowing through the lines that will be compared each and every time interval. For the for the output of the VSM controller, we having a magnitude. That magnitude will be called as a modulating signal. That modulating signal is compared with the pulse width modulation scheme. Then we having pulses. That pulses is going to turn on the IGBT. Okay. So come to the block diagram. This one is the block diagram. This one is the AC microgrid and this one is the DC microgrids. Here we take in DC microgrids, solar and batteries. So here we simply integrating AC microgrids with the DC microgrids. In the place of DC microgrids, we simply place PV panel. You already know how we are generating PV panel. PV power from the PV panel means with the help of the photovoltaic effect. When light radiation and temperature hit the panel, from the hitting of light radiation and temperature, we having the photovoltaic effect. Then we can generate the power from the PV panel. Whatever the generation power from the PV panel, we having low voltages and low currents. Okay. So we need to increase the voltage. How we are going to increase the voltage means with the help of the boost converter. You already know the role of the boost converter is to convert fixed DC to variable DC. How the DC-DC converter will be look like in MATLAB, I will show you here. This is the block diagram for the entire design. So here we are having solar panel and boost converter. This is the boost converter. In boost converter we having MOSFET. So how I am going to turn on this MOSFET means with the help of the MPPT controller here. This is the MPPT controller. From the MPPT controller I am having pulses. So I just open the MPPT controller here. This is the MPPT controller. From the MPPT controller we can generate the pulses. Okay, that is the role of the MPPT. Why we require this pulse means to turn on this MOSFET. Okay, and parallelly we connecting batteries. Why? Because we need to storage voltage for certain time interval, and also we need to deliver power for certain time intervals. How this process will be works on means based upon the bidirectional flow that we mentioned here. Okay, so energy storage system having bidirectional DC-DC converter. That means from here to will the conversion will be takes place, and also from here to also the conversion will be takes place. And which time interval it will be delivers power from the battery means when PV panel is unable to deliver power to the loads. Okay, at that time interval the energy will be whatever the energy storage in the batteries at the time interval. Okay, at the needy time interval the battery need to deliver power to the loads. And which time interval the battery is going to absorb the power from from these terminals means whenever the PV panel having high amount of power. Okay, you know already light radiation and temperature will having high ranges. At that time we having power will be expected than the concerned level. Okay, so at that time the whatever the battery will absorb the power from the terminals. So this is the overall explanation of the DC microgrids. Come to the DC to AC. Why we require DC to AC means we having loads. Whatever the loads we are using here requires AC only. That's why we just need to convert DC to AC. How I am need to convert DC to AC means I will show you the fill. This is the DC to AC inverter. Here we having 6 switches. 6 switches will be IGBT anti-parallel connection of diode. So here also we having IGBTs. Okay, so how we are going to turn on these switches means with the help of the virtual synchronous machine controller and also anti-islanding protection scheme. I already told you na a novel hybrid control scheme will be proposed in this paper. This is the novel hybrid control scheme. Virtual synchronous machine controller with AIP detection. This is the advanced technique. So from this we generating pulses. From these pulses that is going to given to these IGBTs. Then IGBT is going to turn on. Then there will be a currents and voltage will be generated from the terminal sides of the inverter. And whatever the inverter having, when we operate rapidly, voltage stresses and current ripples will be generated. In order to reduce those voltage stresses and current ripples, I am implementing LCL filter here. And then we having circuit breaker CB1 and CB2. Why we require this means I just show you in the simulation results. Okay, there will be a clear explanation in the simulation results. And when we talk about the AC main grids, main grids will be far away from the loads. That's why we just need to mention the transmission line here. This is the transmission line, and the loads, local loads will be connected at this terminal. Okay, and this is the control scheme for the overall virtual synchronous machine control strategy. What are the control strategy that preferred for the virtual synchronous machine means robust droop controller. Okay, robust droop control strategy you proposed in this design. And also we just mentioned the anti-islanding protection scheme, and this scheme will be shown here. This is the anti-islanding protection flowchart and controlling block diagram. I will show you in MATLAB. It is easier to analyze you. So this is the overall robust droop controlling scheme. In subsystem we having anti-islanding protection scheme that is similar to this figure number 3. In figure number 3 we just having this logical operators. That why here also we are using logical operators N and R, and also bistable flip-flops. Okay, so by doing and for conversion of for detection of islanding mode, we required this extra design for the proposed scheme. So come to the simulation results. In case 1, we having reference power. Case 2, connection and disconnection of loads. That means for certain time interval we need to connect the load, and certain time interval we need to disconnect the load. And case 3, we just need to mention a fault. I just mentioned a fault here. A fault time intervals, voltage will be 0 and currents will be attains maximum magnitude. Here we just having magnitude of 40 amperes only. But when fault occurs, at that time the magnitude will be nearly 400 magnitude. I will be show these results in simulation. So the power reference waveform will be like this way. So this is figure number 1. This thing. Okay. Compare here simply. In second case, load connection and disconnection. For load connection and disconnection, I am just mentioning a circuit breaker here. This is a circuit breaker for load connection and disconnection, and the results will be shown in this diagram. When load connecting and disconnecting time interval, you already know the voltage will be same here. When load connecting and disconnecting, whatever the proposed sim voltage having constant magnitude, only changes will be appears across the current only. That means from this time interval we having currents will be low. I will show you these results also. So at the time interval 2.5 to 3 time interval, I having currents less than the previous case. Okay. And third case, we just implementing a fault here for 2.5 to 2.3 2.8 time interval. That means nearly 0.3 seconds. That means only the fault will be takes place for time interval of 0.3 seconds only. Okay. I will just mention the fault. How I am creating fault means with the help of this one. So that's why I am just creating fault. When fault occurs the time interval, voltage will be 0. At the time current will be attains maximum magnitude. Here observe here 400 magnitude, and there will be a changes will in the active and reactive power and frequency also. So in 3 cases we don't having any detection of the islanding. Islanding means main grid is need to separate from the microgrids. Okay, that is the islanding mode. So in these cases we don't have any detection. AIP cannot detect the islanding case. So in below cases, islanding condition will be detected. How this condition will be detected means from the flow chart that we mentioned here. So this is the flow chart, figure number 2. We mention the threshold levels of the active and reactive power. Okay, by according to the power mismatches with the threshold level. For active and reactive power mismatches with the threshold level, then we need to have that condition. What is the condition we have? Islanding detection. Okay, this is the major thing. Islanding detection means I just need to disconnect the main grid with the microgrid. So I just mentioned here the below cases. For 2.5 time interval, I just observe active and reactive power will be changes behind the threshold level. Okay, active and reactive levels will be decreases behind the threshold level. That's why at this time AIP will be detects the islanding mode. Okay, AIP will be detects the islanding mode. So when islanding mode will be activated from this time interval to 0.7 time interval, we need to wait for 0.5 time interval. Why? Because in below 0.75 time intervals, the islanding detection is not going to take place. Okay, you already saw in previous case. In this case, we having a fault for nearly 0.3 seconds. So at this time interval also we having changes in the active and reactive power. Okay, so at this time we don't having any detection of the islanding. Why? Because it just occur a fraction of seconds only. It takes place. Okay, when fault occurs a fraction of seconds, at that time we don't detect any islanding mode. Okay, that is the role of the AIP. So in this case, when fault takes place nearly 0.75 time interval, At that time, automatically the islanding detection will be takes place by the AIP, and IDS will be signal, the command signal. This is the command signal. This command signal will be going to set to 1 when AIP detect the islanding mode. That means at that time the circuit breaker CB2 will be going to operate. Where this CB2 will be takes place in the design. This is the CB2. This CB2, when the CB2 is going to turn on means when AC main grid is unable to deliver the power to the loads. At that time, automatically it detects the active and reactive power that flowing through the terminals, that is given back to this controller. At the automatically it can detect the threshold levels. Whatever the threshold levels will be compared here. When comparison takes place, automatically the IDS signal will be generated. That means the circuit breaker is going to turn on. That means it will be isolate the main grid with the microgrid. Okay, this is the case. I will show you the results of this case. So this is the result of this case. This one. Final case is these two are similar to each other, but we having a slight variation in the active and reactive power. In this condition, whatever the load will be smaller when compared to the power flowing through the terminal sides. Okay, AC terminal bus we having 15 kilowatts, but the load will be only 5 kilowatts. So this condition will be takes place. But in case B, whatever the power flowing through the AC bus, that is nearer to the load power. Okay, so at this time the power will be like this way. At this condition also we need to detect the islanding mode. Why? Because there will be a threshold limit variation in the reactive power. So at this case also we can detect the reactive power, and also I need to show the protection for the entire design. How I am protecting the entire design means with the help of the anti-islanding protection scheme. So when islanding connection is going to turn on, at that time automatically the circuit breaker is going to trips. That means it can isolate the main grid with the microgrid. That is the role of the anti-islanding scheme that is proposed in this control strategy. Okay. So thank you for watching this video.